Welcome back. This is the last and final video in this series of videos that are interrelated on the concepts of electronic configuration, valence electrons, and valence orbitals. Okay. The reason I kept this at the end because this is where the logical sequence should end, because the next most likely topic would be bonding, and it is just so related to the next topic. Okay. Now, this particular video is very interesting because you can have a little competition with a friend at a different school. If they are enrolled in a similar class like you're at a different school, you can just have a quick, a 5-minute challenge between you and your friends and see how the two of you do. I bet you will do better, okay? Because the information that I'm going to present in this particular video is very unique, and it's so fast and so rapid that, your friend might be wondering, how did you get that so fast? What could potentially happen is your friend might actually try to write the entire electronic configuration if they are up to it, or they would just say, I don't know, it's not something I can say quickly. Those are one of the two answers, whereas you will be able to do it because, like I said at the very beginning, a periodic table is an ocean. You can keep digging information out of it. Okay, and I will give you that precious information that you can win your friend over. All right, the tip I've given you earlier is typically metals form cations, and the periodic table is nearly, I would say 95% is metals. Metals always lose electrons, and non-metals tend to form anions, that is, they tend to gain electrons. Okay, there are shortcuts just to determine how many valence electrons that an element can lose or gain. Now keep in mind, what I mean by lose and gain is the job here is for bonding. Okay, an element has to lose to gain some other element's electrons to make a bond. Okay, that's how bonding works. Okay, so ultimately an element has only certain number of electrons available for use, as we saw in the previous video. We cannot just lose as many as we want, or we cannot gain as many as we want, or we can put them anywhere we like. All right, so how can we quickly determine how many valence electron is available for use? Well, if the element is a metal, okay, then the Roman numeral on top of that element column indicate how many valence electrons can be lost. All right, it will make even more sense right away when I do a practice example in the next screen. If the element is a non-metal, then the Roman numeral on top of that column must be subtracted from 8 to determine how many electrons can be added. You may have to go back to the very first video. I'll probably put a link to that video in this video's description. But that video I have pointed out which ones are non-metals. All right. If you all remember what a Roman numeral looks like, I don't think I have to tell you that. All right. So if an element is metal, then the Roman numeral indicates just how many valence electrons can be lost. It's easy when it's metal. When it's a non-metal, all you got to do is take whatever the Roman numeral is and subtract from 18 to figure out how many electrons can be added. Remember, non-metals make anions, metals make cations. Okay. So I'm going to put this. I'm going to work maybe one for each category so you know how to do it. All right. How many valence electrons are there? Say you ask these 6 things to a friend, and they would take probably at least 10 minutes. If they didn't know this trick, it would take very long. All right. If they did know it, then they're going to be very quick. Okay. But that chance is very, 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 very less. Okay. All right. Titanium. You go to the periodic table. Titanium is a metal. Okay. So if you look on the column, it's 4B. Okay, titanium, the column is under 4B. What does that mean? Don't worry about the B, but focus on the Roman numeral. That means titanium has 4 valence electrons that it can lose. If you don't believe me, actually write the valence electron and write the condensed, and then you will see there will be 4 electrons left in that condensed. All right, so go ahead and try for these. Okay, all you have to do is figure out the Roman numeral. That'll tell you how many valence electrons can be lost. This is a metal. So 4 valence electrons can be lost. This is a statement, but in a nutshell, it's the 4 valence electrons. And how many valence electrons can be added to the following nonmetals? Because nonmetals, the Roman numeral, you got to subtract it from 8. So let's take nitrogen. Okay, nitrogen's Roman numeral is 5A. Okay, what we have to do is we have to subtract 8 minus 5, which is 3, which means 3 valence electrons can be added. Trust me, will be a very fun activity. If you want to take on this challenge with your friend, just give them the same 6 or any other 6 elements from metals and 6 non-metals, and have them tell you quickly, like in 30 seconds, hey, tell me how many metals and non-metals, the valence electron count that can be lost or added from a particular element. Well, if they give you that, then they know this, all right? So many people don't even know that took these classes, that why the Roman numeral is there, what is its purpose. They just never learn it, okay? Now, I have given you not everything, but at this point, if you watch this video, I want you to practice out the remaining, all right? This should give you a pretty good understanding of where the course is heading. And then the next logical sequence, as I mentioned, would be the concept of bonding. But again, you gotta first understand what are the valence electrons, because once we start drawing structures, you need to know that information. So this particular video can not only be fun activity with your friends, but personally for you, it should also be an important video in terms of learning about valence electrons. All right? Well, that's pretty much it for this series of videos, and I will see you back with another video on bonding, which would be a very interesting concept. All right? Stay tuned.